We've spent a couple of days, or at least parts of a couple of days, playing with the Van de Graaff generator, where we put somebody's hand on top of the Van de Graaff, their hair stands on end. The question, though, is why? Why does the hair stand on end? Well, it comes down to pretty simple mechanics of the Van de Graaff, actually. What it does is it liberates electrons from essentially the power cord that's coming in. It carries those electrons on this band, okay, this belt that you see going up to the top as you see it spinning around. And then the belt deposits those electrons on the dome of the Van de Graaff generator. So the top of the Van de Graaff generator becomes negatively charged with a massive negative charge, a whole lot of extra electrons. It always had a lot of electrons, but it had a lot of protons as well to balance it out. Now it's got a lot of extra electrons. And those extra electrons cause a charge separation in the hair on your head, which ultimately makes the hair on your head negatively charged. So if this hair is negatively charged, that hair is negatively charged, they want to repel each other, they stand up. Okay, that's how it works. What does the distribution of charge look like, though? Okay, let's look at it on a more fundamental level. We know the electrons go to the dome of the Van de Graaff generator, but what does the distribution look like? Where are the electrons on the dome of the generator? Are they in the inside or are they in the outside? Are they spread out kind of randomly, or is there a pattern to the way they're spread out? That's what we want to talk about today, not just for the Van de Graaff, but for a number of different shapes of surfaces. What does the charge distribution look like when we've got a bunch of extra electrons on there? Well, before we talk about that, we have to define a term: static equilibrium. Who knows what the word static means? Stationary, yeah. If you take engineering at university, one of your courses in your first year will be statics. Okay, statics means, the course, statics means that you're going to analyze stationary things, things that aren't moving. You might analyze the forces acting on a sign that's hanging off of a building. Or you may analyze the forces acting on a bridge when the semi-truck is going over the bridge. The bridge isn't moving, so it's within the realm of statics, versus dynamics, which would be in the realm of things that are moving, right? So static means not moving, at rest. Equilibrium means, biology people might have a better time with this one. Equilibrium means kind of balanced. So what are we talking about here? Well, forces, balanced forces. Object at rest, as Kenton said, or charges at rest with balanced forces acting on them. The reality is, in a conductor, when you have a whole bunch of extra electrons in this conductor, they will repel each other. They'll do that in an insulator as well, but in a conductor, they're freer to move. So the analysis that we're going to do is for conductors. You have a whole bunch of electrons, a whole bunch of extra electrons. They're pushing on each other. They're pushing each other apart. They're going all over the place. But at some point, the forces that repel each other, the repulsive forces, are going to even out. They're going to balance each other. That's when we're in static equilibrium. Equilibrium, balanced forces. Static, well, the charges are going to stop moving around now, because if the forces are all balanced, there's no reason for the charges to keep moving around to attain that balanced force. They're already there. So static equilibrium is when the excess charges reach this point of balancing forces and they stop moving. Okay, that's the goal of a conductor with excess charges, is to reach this point of static equilibrium. Okay, that's the goal of the electrons, to have all balanced forces so that they don't have to move around anymore. But when do they get there? What does the distribution look like when they get to that point of static equilibrium? Okay, we're going to analyze a few different shapes here and see when that point occurs for all of these different shapes. First one's going to be a solid conducting sphere. That's what you see up on the board right now. It's like a marble, except it's made out of metal. It's almost like the Van de Graaff generator, except that the Van de Graaff generator dome is hollow. So that's not a solid conducting sphere. That would be a hollow conducting sphere. This is solid. It's metal or some kind of conductor throughout. Now, in the diagram A here, they've got 3 electrons drawn. Understand that there could be millions of electrons on here, but there's 3 extra electrons. So, for instance, if you have 1,000,000 protons, you've got 1,000,003 electrons. You could have 1 million protons and 6 million electrons. The bigger the object is, the more surface area the object has, the more chance it has of holding on to extra electrons. We're just drawing 3 though. The same analysis would apply even if we had 1 million extra electrons. It's just that the diagram would be a lot more complicated, that's all. Same basic analysis though. Let's take a look at these 3 electrons. Let's name them. Here's electron 1, here's electron 2, here's electron 3. Electron 1 experiences 2 repulsive forces here, or at least if we have 3 extra electrons, 1, 2, 3, it experiences 2 extra forces. If there was 1 million extra electrons, then it would experience 1 million forces. It experiences a force caused by number 2, pushing it down away from number 2, and it experiences a force this way caused by number 3. Force caused by number 2, force caused by number 3. Now, the reality is, the electron doesn't care about the individual forces. The electron cares about the net force. Which way does the net force, the combined force 2 and force 3 point here? Quinn, where do you think that goes? What do you think the net force, if we combine 2 and 3 together, where's the force going to be? To the left? Down and to the left? Down in the middle there? Yeah, good. Somewhere down in there, right? That's the net force. The green force is the combined F2 and F3. Okay, let's do with charge number 2 here. Charge 2 experiences a force caused by number 1 up this way. It experiences a force caused by number 3 up this way. Right, because number 3 repels number 2 and number 1 repels number 2. Ryan, which way is the net force going to act this time? Good, straight upwards. And similarly, on charge number 3, we have a force caused by number 1 and a force caused by number 2. And the net force there is going to be down and to the right. Let's not pay any attention to the red forces now. Okay? Let's pay attention to the green forces that were caused by the red forces. Notice that all 3 of those forces are outward forces. These 3 excess electrons that were inside this conductor get pushed to the outside. They get pushed to the outer surface as a result of repelling each other. Why don't they go beyond the outer surface? They get together and they say, hey, let's push each other away. They push each other away and they go to the outer surface. Hey, stop, don't go any further. Let's stop right here. Let's stop right here on the outer surface. I don't like it out there in that other world. Okay, I want to stay right on this conductor. I want to go to the outside, but I don't want to go past that. Why not? No, good guess though. Yep. There's nowhere to go. What's beyond that most likely? Air. Right? Air is a pretty good insulator, so they don't want to go into the air, right? They don't like going into the air. It's like fish not liking going into the air, right? They stay away from the air. They stay in the water. They might go to the surface, but they're not going any further. Now, if you did, this only applies, right, if you don't have a conductor outside. If you bathed this in mercury, and liquid mercury, then what would happen to these electrons? Well, they'd keep going out, right, into the mercury because it's a conductor. But if it's in air, which is a pretty safe assumption usually, then they're going to go to the outer surface and they're going to stop. Not only are they going to go to the outer surface, look at the distribution of them on the outer surface. They're evenly distributed. So when you got a whole bunch of extra electrons caused by, I don't know, maybe it's carrying electrons on a belt and depositing them just like on the Van de Graaff, or maybe you've rubbed it against something, or it doesn't matter how it got the extra electrons. When you've got a whole bunch of extra electrons, it doesn't matter where they are in this conducting sphere, they will by themselves go to the outside, and they will by themselves become evenly distributed to reach that point of static equilibrium. Does that make sense? Remember, that's the goal, static equilibrium. To get there, they have to go to the outside, and they have to be evenly spaced. Yep, yeah, great. Next picture here. Next shape we have here is a solid, flat plate. It's conducting still. Everything we're going to do here today is based on conductors because this doesn't really apply to insulators so well because it doesn't allow electrons to move around as freely. Solid flat conducting plate. I want you to look at the first diagram here, diagram A. We got three charges in diagram A, charge 1, charge 2, and charge 3. Charge 1 experiences two repulsive forces. It gets pushed away by number 2, but it also gets pushed away by number 3. The force caused by number 2 is like this. The force caused by number 3 is like this. The net force of 2 and 3 combined is the dotted line that they have drawn there. Hey, can anybody explain to me why I've drawn F2 bigger than F3 there? Yeah, cool. It's closer, right? Assuming they're the same value of charge, and they should be because they're both electrons, the closer charge is going to provide a bigger force. So F2 is going to be bigger than F3, but combined, they give me that force that you see right there, the dotted line force. Charge 3, hey, it experiences a force caused by number 1, also one caused by number 2. 2 is bigger than 1 because 2 is closer than 1, but combined, they still only give me this force right here, pretty small force. Okay, why is it smaller than the force on charge 1? Yeah, because charge 2 is further away from charge 3 than it is from charge 1. Here's the real important one, though. Here's the one that we really want to focus on here. It has two forces acting on it. The force of 3 on 2 is to the left. The force of 1 on 2 is to the right. Can anybody explain to me here why F1 is a bigger value than F2? Andy? Yeah. 1 and 2 are quite a bit closer together than 3 and 2. So F1 is going to be a bigger force. Now, what's going to happen to charge 2? What's going to happen to charge 2 as a result of that F1 and F3, F1 being bigger than F3? Charge 2 can move, right? Where's it going to move? James, where's charge 2 going to move as a result of F1 being bigger than F3? Nope. It's going to move to the right. It's going to move in the direction of the bigger force, right? So as it moves to the right, think about what would happen to F1. Think about what would happen to F3. F1 would become, Garrett, smaller, because now you're getting 1 and 2 further away from each other, right? F3 would become right. So F1 becomes smaller, F3 becomes bigger. At some point, as this moves to the right, F1 and F3 are going to be equal in magnitude, right? They're going to be balanced. When are they going to be balanced? When it's halfway between. That's when they're going to stop. That's when in that state of static equilibrium, charges have stopped moving now because the forces are balanced. Where are those charges? Well, A, they're on the outer surface because it doesn't matter what the shape is, they're going to go to the outer surface. B, they are once again evenly spaced or evenly distributed on the outer surface. Does that make sense? Now, one quick little thing here. Let's go back to this one just for a second. In diagram B, you got some field lines drawn towards the individual charges, which gives us a net field toward a negative producer. We call that a non-uniform field because the lines aren't equidistant apart. Here, the individual field lines are also pointing toward the individual electrons. Because the electrons are evenly spaced, the field lines will be evenly spaced. Because they're evenly spaced and it's flat, the field lines will be parallel. This gives us a uniform electric field versus the non-uniform that we had in the last diagram. Got it? Okay, couple more, but the next one is, this one is the last kind of hard one that we have to go over. The next one that we go over after that is pretty much the same as what we've already done. This This time we have an irregularly shaped object. It's like a pointy thing. It's like you got this metal roof on a building, and there's a lightning rod sticking up out of that metal roof. Or you've got this big machine with this pointy metal thing that's a part of this big machine. An irregularly shaped object with something kind of pointy. I want you to look at the first diagram, and I want you to scratch out that fourth charge. If we keep it there, we don't get different results. It just makes the analysis a little bit harder, and we don't really need it. So let's take a look at the first three, and let's label them. 1, 2, and 3. Charge number 1 pushes charge number 2 away. We're going to call that the force of 1 on 2. Charge 3 pushes charge 2 away. We're going to call that the force of 3 on 2. Right, Parker? All right. There are other forces that act on charge 2 as well as a result of other charges like charge 4, but we don't need those. We don't need to worry about those. Okay, we get the same results if we just focus on those two. Take a look at F3 first of all. It can be broken down into two components, an X and a Y. The Y component of F3 pushes that charge to the outer surface. If you got a whole bunch of extra electrons that are in this pointy shaped object, where are they going to go? To the outer surface. Okay? The Y component of F3 pushes it to the outer surface. So we know they go to the outer surface. Now, where do they go on the outer surface? Okay, on the solid conducting sphere, they were evenly spaced. On the flat conducting plate, they were evenly spaced. What about this? Well, we want to look at F12 in the X component here to look at where they're going to be on the outer surface. The Y component gets them to the outer surface. These two determine where they're going to be on the outer surface. Which one's bigger, F1 or the X component of F3? I think that's pretty clear, right? Which one's bigger? F1. So, as a result of F1 being bigger, charge number 2 is going to be pushed more towards the point here, right? But as it gets further away from charge 1, F1 is actually going to get smaller. At some point, F1 will balance out with the X component of F3. So at some point, it's going to stop. It's going to be in static equilibrium. But that point's going to occur not when the charges are evenly spaced, but when the charges are kind of pushed toward the tip, like they are in this diagram. We don't have an even charge distribution here. This time, we get a higher concentration at the tip. Now, I know your finger's not a particularly great conductor, okay, but I'm still going to use this analogy here because you've all done this, you've all experienced this. You walk across the carpet, you charge your feet, you charge your body by friction. We walk up to somebody and we want to shock them. How do we do that? Do we stick out the side of our arm like this and try to shock Shailene like this? No. No, that doesn't make any sense. Intuitively, we know that we don't do that, right? So what do? Right, you stick out your finger. You stick out your finger and you try to shock her. Why your finger as opposed to the side of your arm or the side of your leg or your hip? Okay, why your finger? Because you got a bigger charge buildup at your finger than you do on flat parts of your body. Right? Your finger is pointy. It's a stronger charge buildup there because charges naturally gravitate to pointy things, like your finger. Same thing with a lightning rod. Here you see a metal roof, but then you see this lightning rod sticking out. What's the lightning rod there for? To encourage lightning to strike. We want it to strike here. where we can attach a ground wire and run it down through the ground. We don't want it to strike the rest of the building. We want it to strike here. Why does that pointy thing work? Because it allows a higher charge distribution, a higher charge concentration on the pointy thing than it does on the flat or uniform surface. Does that make sense? Okay, one more diagram, and I'm going to show you a little video, okay? Good news is, we're past the hard part. This is a hollow conducting object. This is the Van de Graaff generator, the static ball that we've used earlier in this unit. This is almost the same thing as a solid conducting sphere. Almost the same thing, except it's hollow. Charges still go to the outside for the same reason. Charges still get evenly spaced for the same reason. The charge distribution looks exactly as it does on the solid conducting sphere, except it's hollow. We call this a Faraday cage. A Faraday cage is a hollow conductor. It allows, well, let me draw a little bit more to this diagram, then I'll tell you what it allows. Notice the electric field lines are drawing toward the negatives. Of course they are, right? But if we're looking at it on the inside, the electric field lines would be pointing this way towards the negatives. Those three electric field lines that I've just drawn cancel each other out. The net electric field is 0. Okay, that's what's important about this. The net electric field inside this Faraday cage is 0 newtons per coulomb. Why is that important? Why is a car a safe place to be in a lightning storm? We've all heard that before, right? Is it an urban myth? An old wives' tale that a car is a safe place to be in a lightning storm? Absolutely not. It is 100% correct. There is very few places out there that are safer than a car to be in a lightning storm. There are things that are equally as safe as a car, but can't think of one that's safer than a car in a lightning storm. That doesn't mean your car's not going to get struck by lightning. It could. It could. Cars do get struck by lightning. Not that often, but they do get struck by lightning. Why is it safe, though? Well, because your car is a Faraday cage. It's a hollow conductor. In a hollow conductor, excess electrons end up spreading out around it, giving us a net electric field inside of 0. If there's no electric field inside, then you can't be electrocuted. Does that make sense? The charges go to the outer surface. They may not be completely evenly distributed because the car is not a nice uniform shape as much as we've drawn here. But the net electric field will still be 0 inside. And if the net electric field is 0, you can't be electrocuted. You feel no effect whatsoever because there's no electric field. That makes sense? Everybody thinks it's because of the tires, right? Rubber's an insulator. Well, the electrons aren't going to come from all these electrons that came from lightning. They're not going to go from the car to the ground because it's insulated by rubber. Listen, the electrons just made it from the cloud to your car. You don't think they can go from your car to the ground? Forget about the rubber. They can go through the air from your car to the ground. And they do. They do discharge from the car to the ground. But it doesn't matter because you're inside and the net electric field is inside. You're in a Faraday cage.